We'll see. Okay, so yes, this is joint work with my co-authors Xi Chen, Bishal Deb, Alex Dyachenko, and Alan Sokol. And where does the story start? We start with the Eulerian Triangle. So this is an infinite lower triangular matrix with integer entries. The entries are defined, they satisfy a linear recurrence. The n-kth term is n minus k times the n minus 1 k minus 1th term plus k plus 1 times the n minus 1 kth term. And the n-kth entry of the Eulerian triangle counts permutations of the n set 1 to n with k descents or k ascents. And you can find it in the OEIS. This is its reference number here. I'm actually going to talk about the clean Eulerian triangle. That's the triangle obtained by deleting the first row of the Eulerian triangle that I showed on the slide before. So there's linear recurrence is slightly modified. There's a +1 here. And the entries of this matrix count permutations of the n plus 1 set with k descents. A seemingly innocuous lower triangular matrix. The interesting thing about this matrix is in 1996, Brenty conjectured in a paper about total positivity that this triangle is totally positive. What do we mean when we say a matrix is totally positive? A finite or infinite matrix with entries with entries that are real numbers is totally positive if all of its minors are non-negative. So you take this infinite matrix, you look at all possible minors of it, and if they're all non-negative, then your matrix is totally positive. So this was conjectured back in 1996 by Brenty, so over a quarter of a century ago. And as far as we know, it's still open. It's yet to be proved. And what I'm going to talk about today is some generalizations that we came across while trying to prove this conjecture. In the time-honored mathematical tradition of generalizing in order to specialize, we came up with a new matrix, which we call TACDEFG, which I'll tell you about now. So we tried to prove the Eulerian triangle was totally positive, and we were led to this much more general matrix, TACDFG. This matrix is defined by the following recurrence. So we've got n minus, so it's a 3-term recurrence. The n-kth entry is, this sum of the n minus 1 k minus 1th entry, n minus 1 kth entry, and the n minus 2 k minus 1th entry with these initial conditions. Here the A, C, D, E, F, and G are treated as algebraic indeterminates. They could in principle be anything, but we treat them as algebraic indeterminates. So the entries of this matrix belong to this polynomial ring. And this matrix ACDE essentially defines a family of integer matrices. What I mean by this is if we specialize any of the values A, C, D, and E, any of the indeterminates A, C, D, E, F, G to integers, we get various integer matrices that are of interest. For example, the if we set A, C, D, and E to 1, we obtain the clean Eulerian triangle. If we set C, D, and E to 1, we get something called the Stirling subset triangle. The entries count partitions of the set 1 to n plus 1 into k non-empty blocks. And
excuse me, very quick question. In all these cases, you basically get, after the specialization, a 2-term recurrence, right? That is to say, the new t will depend only on 2 previous t's. Am I right?
Not in the third case here. If we set C, F, and C, E, and G to 1, we get the Delanois triangle, which is a 3-term.
Really involves 3. Okay, but the first 2 involve only 2 each.
Yeah, exactly. But there's no reason why you can't have this. We have the Delanois triangle here if we set these, if you set C, E, and G to 1, right, and everything else to 0. So this is the matrix that we're interested in. This is the first 4 rows and first 2 columns. They're these sort of big polynomials. What is this? How do we think about total positivity in terms of matrices that have polynomial entries, though? So far, I've only talked about it in terms of matrices with real numbers, real entries. but there's a way to extend the notion total positivity to a matrix with polynomial entries. So you first have to equip the polynomial ring with a coefficient-wise partial order. So when we do that, basically a polynomial in this ring is non-negative if it's a polynomial with non-negative coefficients. And this is how we write that. Okay, and then you can extend the definition of total positivity to matrices that we call coefficient-wise totally positive. So matrix with entries in this polynomial ring. Here, boldface X means just a set of indeterminates. So if your matrix has entries in this ring, it's totally coefficient-wise totally positive if all of its minors are non-negative polynomials. And it turns out, as far as we think that this matrix that we defined is coefficient-wise totally positive. So it's a matrix with these complicated polynomials. There's sort of 6 different indeterminates in there. And as far as our experiments can say or tell us, this matrix looks to be totally positive, coefficient-wise totally positive. This is the conjecture we arrived at. We tested it to, I think, 13 by 13, which is understandably fairly modest. However, that took something like 6 months of computing time to check that all of the minors of this were non-negative polynomials. So we're partly sure that this might be coefficient-wise totally positive. We've yet to prove it, though. It's incredibly complicated. It seems incredibly complicated to prove this conjecture. What we have proven is that the matrix obtained by setting D, F, and G to 0, so that's a matrix with 3 indeterminates A, C, E. This matrix is coefficient-wise totally positive. And for the rest of the talk, I'm just going to talk about how we prove that. So from now on, I'm going to let T, A, C, E denote this matrix with D, F, and G set to 0. So how do you go about proving total positivity and proving coefficient-wise total positivity? There are a couple of different approaches. We have a much longer paper, which contains about 3 different proofs of this theorem so far. But given the nature of this conference, I'm going to talk about the approach that's slightly more combinatorial. And the way that one way you can prove total positivity is using things called planar networks. So here's a slight digression into digraphs and planar networks. So think about a locally finite acyclic digraph. It has a set of sources, U1 to UN, and sinks V1 to VK. We assign to each edge in our digraph a weight that belongs to some commutative ring. The weight of a path from UN to VK is the product of the weights of its constituent edges. And we can form, given a digraph such as this one, we can form the path matrix where the nkth entry is the sum over weighted paths from UN to VK. As I'm sure many people in this audience will know, there's the Carlin, McGregor, Lindstrom, Gessel, V&O lemma. So given any digraph such as this, the KMLGV lemma says that if you take the determinant of the path matrix, this gives you a signed sum over weighted families of non-intersecting paths. So the weight of a family of so P1 to Pn is a family of non-intersecting paths. The weight of this family is the product of the weights of the paths, and the determinant gives you this signed sum over these families of paths. This is all very well known. There's an extra condition you can think about when you come across locally finite acyclic digraphs, and that's the concept of full compatibility. So if you have a digraph with sources and sinks, the sources and the sinks are fully compatible if they satisfy this definition here, but in a hand-wavy way, the sources and sinks in your digraph are fully compatible if, when you traverse the outer edge of the digraph, you read first the start or the source vertices in order, U1, U2, U3, U4, and then you read the sink vertices in reverse order, V4, V3, V2, V1. So if your sources and sinks satisfy this property, then your locally finite acyclic digraph is fully compatible, or the sources and sinks are fully compatible, and we call a planar network a locally finite acyclic digraph with fully compatible sources and sinks. What does this have to do with total positivity? Brenty observed in his 1996 paper, I think, that that if you have a locally finite acyclic digraph and U and V are fully compatible, then every minor of your path matrix is a sum over weighted families of non-intersecting paths. What does that mean? Well, if all the edges in your digraph have weights that are real numbers and non-negative real numbers, then your path matrix is immediately totally positive. And moreover, if all of your edges have weights that are polynomials, non-negative polynomials belonging to some polynomial ring equipped with a coefficient-wise partial order, then your path matrix is immediately coefficient-wise totally positive. And if you needed another reason to love the LGV lemma, then here it is, right? You can just draw yourself any locally finite acyclic digraph that's fully compatible with planar network. You just attach any polynomial weights to it, polynomials that are non-negative from your chosen polynomial ring, and you immediately have a matrix that is coefficient-wise totally positive. I think that's like a really beautiful aspect of this LGV lemma. The question is, you can obviously come up with any digraph you want, but how do you find one that corresponds to the matrix that you are interested in? Let's go back to the matrix ACE that I mentioned before. So here's the definition. It's a two-term recurrence. We've got A times n minus k plus C times T n minus 1 k minus 1 plus E times the n minus 1 kth entry with these initial conditions. Now, this matrix has a combinatorial interpretation, which is in our extended abstract. Essentially, the entries of this matrix are they are the weighted count over partitions of an n plus 1 set into n plus 1 minus k non-empty blocks. And the weight of each partition is the product of the weight of its elements. And the weights of the elements are defined here. So we found a combinatorial interpretation of our matrix in terms of weighted set partitions. There's a second, perhaps arguably more simpler way to interpret some of these matrices, matrices defined by this linear recurrence, and that's in terms of walks in the quarter plane. So the nkth entry of TACE is the sum over weighted walks from the origin to the point with coordinate nk in the upper quadrant, upper right quadrant. This is relatively easy to see. Let's pick this point here, 3, 1. How can we get to 3, 1? What are all the different ways we can get to 3, 1? Well, we can take all the walks to 2, 0. So that's the n minus 1 k minus 1th term. And we multiply them all by a times n minus k plus c. That's this diagonal edge here. Or we can go instead to this point here, 2, 1, and take the horizontal edge to get to 3, 1, and that's the e n minus 1 kth term here. So there's a simple way to see this as walks in the quarter plane. And looking at this, you might think, well, this is easy. Here we've got like a locally finite, this here on the left is certainly a locally finite acyclic digraph. However, it's clearly not a planar network because all of the endpoints are here and they certainly don't satisfy the full compatibility condition. The sources and the sinks are not fully compatible. So the challenge when you want to prove something like this is to find a network where you have these distinct start points and distinct endpoints, and your digraph is your locally finite acyclic digraph is also a planar network. So sometimes with these recurrences, it's quite easy to do. Brenty pointed out that in situations where, for example, your linear recurrence is purely k-dependent, then there's a relatively straightforward translation from this walks in the quarter plane to this a digraph that looks like this over here. These alpha and beta weights are relatively straightforward to find. Similarly, if your linear recurrence is purely n-dependent, there's also a straightforward translation from your walks in the quarter plane to a digraph such as this. Sorry, a planar network such as this. The weights are quite easy to find. But when n and k are mixed, when you've got a linear recurrence that's dependent on both n and k, it becomes much more complicated. You start to play around with this picture over here, and it becomes very difficult to figure out what these alphas and betas might be. But we did eventually find it for our matrix TACE. And this is what it looks like. We have these start points, U4, U3, U2, U1, U0 along the bottom here, and these endpoints, V0, V1, V2, V3, V4 up on this diagonal here. Every green edge has weight C, every red edge has weight E, every blue edge has weight A, and every black edge has weight 1. And you have to imagine, I haven't drawn the arrows, but you have to imagine all the edges are directed to the right and up in this digraph. Sorry, this is planar network. So we found this planar network, but the question is, how do we prove that this planar network corresponds to the matrix ACE? One way you can do that is perhaps by looking at the recurrence. So ACE satisfies this linear recurrence, as we saw before, but it's not clear. It's not clear that it's not easy to see for me, how this recurrence appears within this planar network. But it turns out that using our combinatorial interpretation, in terms of set partitions, we found a different recurrence for ACE, and that's this one here. So C times the n-1 k-1 term plus this sum over some binomial coefficient, ACME T n-1 minus m k-m with these initial conditions. And it turns out that this recurrence is the one that we need. So I'm going to briefly sketch how this planar network satisfies this recurrence. Let's look at all the ways we can get from the source U4 to the sink VK. What we can do is first go up this green edge here. That has a weight C. So we get to this point here. And then we have to look at all the ways to get from this point to VK. But this whole network here is isomorphic to the network we see down here. So that gives us the first term in our recurrence. Right, going from here to VK is the same as going from U3 to VK minus 1. All right, next we can go to the right from U4 to U3. When we do that, we pick up an edge of weight E, and then we have to look at where we can go from U3. So we go from U3 to VK, right? If we want to go from U4 to VK minus 1, sorry, VK, we can go down this and then go to the VK here, right? Next, we can go to the right from U4 and then take one of these blue edges here. That gives us a weight A. We then travel horizontally to this point here, which gives us a weight E. And then all the paths that go from this point to some endpoint, which would be the VK minus 1 vertex. This part of the digraph is exactly isomorphic to this part of the digraph down here. So we get the number of paths from the weighted sum over paths from U2 to VK minus 1. Similarly, to get to this point here, we can first take two edges of weight A. So there's 3 choose edges of weight A. We then get an edge of weight E. And then we have to go from this point to here, which is exactly repeated down here. That gives us the U1 VK minus 2 term. And then finally, we can take choose 3 alpha edges, power 3, along an edge of weight E. That takes us to V3. And this point here is exactly the same as this point here. I should say the number of paths from a start point or an end point to itself is 1. That's like just a convention that we employ. So this is precisely, so the paths in this network satisfy this recurrence, as I loosely explained just now. there's my timer. And this recurrence is precisely the same recurrence that I showed you before for ACE. So that's how we go about, that's one way that we go about proving this particular theorem. And if you'd like to read about it, please do take a look at our extended abstract. We do have a much longer paper that's under construction. I'm not sure when it will be publicly available because we're intent on proving this conjecture that I showed you before. We've proven it for these three indeterminates, ACE. The question now is, how do we just put these extra ones in? Like, how do we put, how do we add a D, an F, and a G into our planar network? And that seems incredibly tricky to do. I have a whole collection of different networks and digraphs that I've drawn, but I haven't been able to, we haven't together been able to pin down anything further than ACE until, well, yeah, so this is ongoing work. And so, yeah, that's basically what we're about. If anyone wants to take up the mantle and join in trying to find these planar networks or has an idea on how to maybe push this in a different direction, I'd be very happy to hear from them because it's been torturing me somewhat for the last 2.5, 3 years. So yeah, I'll stop there. Thanks very much.
Thank you very much. Thank you very much for this fascinating talk. We had some questions during your talk, but it seems that we have a question and an answer. The questions was, if A equals C equals E equals to 1, what are the numbers in the matrix? And it seems that the suggested answer from the audience was, this should be the Stirling numbers of the second kind.
If A, C, and E equal 1.
That's right.
And everything else is 0.
That's not clear from the question.
Okay. So if A, C, and E are 1, then the matrix you obtain is what we call the reversed Stirling subset triangle. So there's the Stirling subset triangle, the n-kth entry counts partitions of n+1 into k non-empty blocks. But if A, C, E are 1, then essentially we take the reversal of that. So it's the entries are the number of partitions of the n+1 set into n+1 minus k non-empty blocks. This was on my slide. Yeah. So I didn't talk about the notation because of time, but pi nk is the partition of the set, n+1 set into n+1 minus k non-empty blocks. So if all these weights are set to 1, then that's what it counts.
Do we have some more questions? We have a question from Olivana. What happened to the letter B?
What happened to the letter B? Yes, very good question. We originally had a letter B, and the B was next to this. There was a B plus K in this term here. It was A n minus K plus B K plus C, and we computed it, and it looked like it was totally positive up to 12 by 12. And then all of a sudden at 13, 2 months later, when we got to 13 by 13, it broke. And so we had to remove the B. And then we never changed the letters then because it was already set in our heads.